Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today, we will discuss the optical flow. Here are the contents. Optical flow is a technique in computer vision that describes the pattern of apparent motion of objects in an image sequence. It is calculated based on the movement of pixel intensities between two or more consecutive frames. Optical flow assumes that object motion between two frames is small and that pixel intensities remain constant over time. In essence, optical flow helps us understand the motion dynamics within a scene by estimating the displacement of objects or features across frames. This is crucial in numerous applications, including motion tracking, following objects in a video sequence, video stabilization, correcting for unwanted camera movements, 3D reconstruction, estimating depth information and scene geometry. The core of optical flow is the brightness constancy assumption, which states that pixel intensities in a scene do not change between frames, i.e. Ix, Yt, Ix plus X, Y plus Y, T plus Det, Ix, Yt, Ix plus on delta X, Y plus on delta Y, T plus on delta T, where 2 represents the pixel intensity at position, X, Y, and time Tt. The optical flow equation can be derived by considering the spatial and temporal derivatives of the image intensity. This equation links the motion components, UU and VV, which represent the flow in the x and y directions. XU plus IV, that 0 and frac, hinsian partial, I2 quasum partial x, U also plus munch frac, insian partial, I2 no mar partial y, V plus so no frac no mar partial, E mar partial, hence 0, here, x and frac U mar partial, I show no partial, x and I frac, mar partial, I some mar partial. You represent the image gradients in the spatial directions, while ek frac mar partial I bar r partial t represents the change in intensity over time. Optical flow algorithms rely on several assumptions to compute motion vectors. Brightness constancy. As mentioned earlier, this assumes that the pixel intensity of an object does not change between frames, which holds well in most scenarios where the object's appearance remains constant. Small motion. The motion between frames is assumed to be small enough to use linear approximations. This assumption breaks down in cases where the motion is large or when objects experience abrupt movements. Spatial coherence. Nearby pixels generally exhibit similar motion. This assumption is especially important in homogeneous regions where there are no significant texture variations. Local smoothness. The flow is assumed to be smooth within small regions. Sharp discontinuities in flow are generally treated as noise, and additional methods may be used to handle them. These assumptions simplify the complex task of computing optical flow, but also limit its application in cases where the assumptions are violated, such as in high-speed motion or scenes with large illumination changes. There are several methods for computing optical flow, ranging from traditional algorithms to deep learning-based approaches. Lucas-Kinnaid method. This is one of the most popular methods for optical flow estimation. It assumes that the flow is constant within a local window and uses image gradients to compute the motion vectors. It is efficient and works well for small motions. Horn-Schunck method. This approach uses a global smoothness constraint across the entire image. It solves the optical flow equation using variational methods, assuming smoothness of the flow field. This can lead to better results in cases of larger motions, but is computationally more expensive. Block matching. This technique divides the image into blocks and tracks each block's movement across frames. It is commonly used in video compression and is simple to implement but computationally intensive. Deep learning-based methods. Recently, convolutional neural networks, CNNs, and other deep learning models have been employed to predict optical flow. These methods can learn complex patterns in the data and handle nonlinearities in motion, providing more accurate results for challenging scenarios, such as large motions or complex scenes. The Lucas-Kinnaid method is one of the most widely used optical flow algorithms due to its simplicity and efficiency. It is based on the assumption that the motion of objects within a small neighborhood is constant. This allows us to approximate the flow for each pixel by solving a set of linear equations that are derived from the image gradients. In essence, for each pixel, the method estimates the flow by analyzing the motion of neighboring pixels within a local window. The flow vectors are computed by solving the system of equations. AV vect BA hand C dot V in dot B, where AA contains the image gradients and VV is the vector of motion. This method works well in situations with small motions and simple backgrounds. The Lucas-Kennard method is fast, making it suitable for real-time applications, such as object tracking or visual odometry. The Horn-Schunck method is a more global approach to optical flow estimation. While the Lucas-Kennard method assumes constant motion in small local windows, Horn-Schunck imposes a smoothness constraint on the entire image. This means that the method expects the flow to vary smoothly across neighboring pixels. Horn-Schunck solves for the optical flow by minimizing an energy functional that consists of two terms: a data term, which ensures that the brightness constancy assumption holds, a smoothness term, which penalizes large variations in flow between neighboring pixels. While this method provides more accurate results in the case of large motion or complex scenes, it is computationally expensive compared to the Lucas-Kennard method. Block matching is a simpler method for optical flow, often used in video compression and motion estimation. This approach divides the image into small, non-overlapping blocks and tracks their movement from one frame to the next. For each block, the algorithm searches for the best match in the next frame using a similarity measure, e.g., sum of squared differences or normalized cross-correlation. Block matching works well in high-motion scenarios and where the motion is relatively uniform across regions. However, it can be computationally expensive when applied to large images and does not handle finer, pixel-level motion well. It is more suitable for tracking the movement of larger objects or in video compression, where block-based analysis is common. In recent years, deep learning has significantly advanced optical flow estimation. Convolutional neural networks, CNNs, can be trained to predict the optical flow directly from pairs of images. These deep learning models are trained on large datasets and learn to capture complex motion patterns, handling large motions, occlusions, and intricate scene structures much better than traditional methods. For example, FlowNet and PWCNet are two popular neural network-based models for optical flow estimation. FlowNet uses a fully convolutional network to predict flow, while PWCNet introduces pyramid networks and cost-volume techniques to improve performance for large motions and better efficiency. Deep learning-based methods are especially advantageous in complex and real-time applications, such as autonomous driving and action recognition. Optical flow has numerous practical applications in computer vision and robotics. Object tracking. Optical flow can be used to track the movement of objects across frames in a video sequence. By computing the flow between consecutive frames, we can determine the trajectory and position of objects. Video stabilization. Optical flow is widely used in stabilizing shaky video footage. By analyzing the flow of motion in a video, the camera motion can be estimated and compensated for, resulting in smoother video. Depth estimation and 3D reconstruction. Optical flow can provide insights into the depth and structure of a scene by estimating the disparity between different objects' motion in the image. Autonomous driving. In self-driving cars, optical flow is used to track the motion of nearby vehicles, pedestrians, and obstacles, enabling decision-making for safe navigation. One of the important applications of optical flow is depth estimation. By analyzing the relative motion between the camera and objects in the scene, we can infer the depth of various objects. Specifically, the amount of motion, disparity, observed for each object is inversely proportional to its distance from the camera. In stereo vision or monocular depth estimation, optical flow helps us create 3D reconstructions of the scene. This is particularly useful for autonomous driving, where depth information is crucial for understanding the spatial relationships between objects and the vehicle. While optical flow is a powerful technique, it faces several challenges. Large motion. When the motion between frames is large, the linear assumptions used in optical flow methods break down, leading to inaccuracies. This is particularly problematic when tracking fast-moving objects or large camera motions. Occlusions. When objects move behind other objects or go out of the camera's view, occlusions occur. Estimating optical flow in such situations is difficult because parts of the scene are not visible in the subsequent frame. Illumination changes. The brightness constancy assumption holds only when there are no significant lighting changes between frames. Illumination variations, such as shadows or reflections, can interfere with accurate flow estimation. Computational cost. Deep learning methods for optical flow estimation can be computationally expensive, requiring substantial resources for training and inference, which can be a limitation for real-time applications. To overcome some of the challenges in optical flow estimation, several strategies can be employed. Multi-scale techniques. Using multiple scales helps in handling large motions by estimating the flow at different levels of resolution, starting with coarse estimates and refining them with finer scales. Robustness to occlusions and illumination changes. Modern algorithms use techniques like adaptive filtering or neural network-based regularization to deal with occlusions and illumination variations. Deep learning integration. Combining traditional optical flow methods with neural networks enables more robust and accurate flow estimation, especially in difficult scenarios. Temporal consistency. Using temporal consistency across frames can help improve tracking and reduce errors due to large motion or occlusions. The future of optical flow is looking towards more advanced and efficient techniques. Real-time flow. As autonomous systems and robotics demand faster decision-making, real-time optical flow estimation will be critical for applications like self-driving cars and drones. Multimodal fusion. By combining optical flow with other sensors, such as LiDAR, depth sensors, or even radar, systems can achieve more accurate and robust motion estimation. Few-shot learning. Few-shot learning techniques could help train optical flow models with minimal data, which would be beneficial in specific domains like medical imaging or specialized industrial settings. 3D scene reconstruction. The integration of optical flow with depth estimation techniques will play a vital role in 3D scene reconstruction, contributing to enhanced scene understanding and augmented reality applications. Optical flow is a powerful tool in computer vision, enabling machines to estimate motion and track objects across frames. The core algorithms, including Lucas-Canada and Horn-Schunck, have evolved to handle more complex motion estimation through deep learning-based methods. The applications of optical flow are vast, from object tracking and video stabilization to 3D scene reconstruction. As technology advances, we will see optical flow algorithms becoming more efficient, accurate, and integrated with other sensor data for better performance in real-world scenarios. The future of optical flow is bright, with potential breakthroughs in real-time processing, autonomous systems, and enhanced scene understanding.